We're going to look at the equation of a line, but the vector equation of the line. So how do we write the equation of a line in vector form? So we'll start off in 2 dimensions, and then we'll push that idea through to 3 dimensions. So here we go. There's our standard coordinate axes. We've got our red vector there. I want to find the equation of it. So I've drawn in 3 points. So A and B are points that I know are on the line. R is just some random point on the line somewhere. So if R is on that line AB, then I know vector AR is some scalar multiple of vector AB. In this case, that scalar would be less than 1, the way I've drawn that diagram. Now vectors are head minus tail. So AR would become R minus A. And then it's a scalar multiple of B minus A. Now the vector R is what I'm finding an equation for. So moving the A to the other side, I get the formula right there. That is the equation of a line. So vector equation of a line is R equals A plus some scalar multiple of B minus A. It is actually quite similar to Y equals MX plus B. It's sort of the same idea, because we're saying, well, mx, 2 things multiplied together, m in that case is the slope, but in this case we've got lambda times b minus a. But let me show you how we can come up with the equation of a line from that. So if a and b are the points x1, y1, x2, y2, if I now write my vectors in column form, then R is just the point I'm talking about, so that'll be xy. And it's going to be the vector A. Now, because I've joined them all to the origin, that makes life nice and easy. So we've got x1, y1, and some lambda times, and again, it's head minus tail. So B minus A is x2 minus x1, y2 minus y1. Okay, now if I was to break those up into the parametrics, essentially now we have parametric equations of the line. I've got an equation for the x value, I've got an equation for the y value. Rearranging that, we get something strange. If I make lambda the subject of both of those, and then, so for the x's I get x minus x1 over x2 minus x1. But for the y equation I get y minus y1 over y2 minus y1. Well, they both equal lambda. So if I play around with that, there's, by the way, that's the Cartesian equation of the line. The fact that it equals lambda, yes, that's a little bit different, having it equal to something else. But watch what happens if I deal with the first 2 bits. If I cross multiply, look what we end up with, the point slope formula. So we can get back to what we're used to seeing for the equation of a line from the vector equation of the line. So now, how do I write the equation of a line if I know it goes through these 2 points, but I just want to write it as a vector equation? I can just write it straight down. Whoa, where did he get all these numbers from? Okay, xy, obviously, because that's the r, if you like, the r vector. Now, it's any point on the line I can write in there. So it's told me it goes through 3 minus 5 and minus 2 minus 8. I just chose 3 minus 5. I could have done minus 2 minus 8, doesn't really matter. Some scalar multiple of, and this is what's like the slope of the line, if you like. So I could have also written it, as I say, as with minus 2 minus 8 there. Now, how do you set that up? Have a look. There's the Cartesian equation of that line if I'd worked it out. It would have been y equals 3/5 x minus 34 and 3. Well, the 34 and 3 doesn't really matter. What I'm interested in here is the slope. See how the slope of the line's 3/5? Now have a look at that vector that's multiplied by lambda. So effectively, that's your slope of the line. It's written a little bit differently because, of course, we're not used to seeing a slope with the x value on top. But that's not a fraction, I'm not saying it's 5/3. I'm saying it's the vector 5, 3. So it's a direction vector. It's telling you what direction it's going in. All right. Just as an aside here, what we saw in complex numbers, you'll recall, rotation of a vector 90 degrees turns out to be a multiplication by I. So, what I could say, the vector, given what we just saw about slope, how it relates, my vector would be run over rise, right? Because the actual slope would be rise over run, of course. So run over rise times I I'm multiplying that vector times I. Then I get I run minus rise. Okay? Now, if I write that back into vector form, minus rise over run. So in other words, those two vectors, run over rise and minus rise over run, they're perpendicular to each other. Because if you did the dot product, you would in fact get 0. You would in fact get 0. So it's, I guess, a little proof there, but using vectors to prove that idea. Okay, as I say, that's just an aside. So what would the vector equation be for this particular line? Again, I can now just write it down, because I can pick any point I like on the line to be that first vector. So I've chosen minus 2, 1. Then it's going to be a scalar multiple of the direction vector. The slope of that line is minus 2/5. So when I write it as a direction vector, it's 5, negative 2. So again, the first one can be any point that lies on the line. So there's an infinite number of answers for this. And then the direction vector, well, it looks like, it's not actually a fraction, but it looks like it's the reciprocal of the slope. Okay, so now we've got another way of finding the point of intersection of two lines. We can use vectors. So my first one would be, again, I can pick any point on the line. I'm going to make life easy for myself. I've chosen the y-intercept. So 0, negative 1. And then a scalar multiple of the direction vector, so 1, negative 2. The second line would be, I've chosen the x-intercept this time, 3, 0, plus, now I can't guarantee it's going to be the same scalar multiple, so I need a different symbol. I've just used mu instead of lambda for this one. And the slope, or the direction vector, 5, negative 3. I want to find when these things are equal. So I can look at the different components. So if I read across the x's, I know that lambda will equal 3 plus 5 mu. Now if I read across the y components, I get minus 1 minus 2 lambda is minus 3 mu. And that's what I'm solving simultaneously. So I end up with mu equals negative 1. So I now know mu is negative 1. I can just sub it back in. Well, it makes sense to use the second one there. So it's going to be 3 0 minus 5 minus 3. So my point of intersection is negative 2, 3. Is that quicker? I suppose it depends on the numbers. Oh, you still got to solve something simultaneously to get it. All right. This time we're going to find a vector equation. It's going to join the points minus 1, 1 and 4, 11. From that, we're going to write parametric equations for any point on the line. And then work out where that line meets the parabola y equals x squared. Okay, so first thing, vector equation. Again, we can just write it down. I can pick any point I like. I thought minus 1, 1 is probably easier to work with than the other one. And the slope turns out to be 2. So we get lambda times the direction vector. So use that to write the parametric equations. Well, that's just reading across the lines. So x will be minus 1 plus lambda. Y is 1 plus 2 lambda. The parameter is lambda. We want to know when it intersects y equals x squared. So I sub in those parametrics into y equals x squared. We can work out what lambda is. So 1 plus 2 lambda is minus 1 plus lambda squared. We end up with two possibilities. Lambda is equal to 0 or lambda equals 4. Well, they will represent the two different points that line cuts the parabola. So it's now just a matter of substituting back in, and we get minus 1, 1 and 3, 9 for the point of intersection. We'll now push that idea through to 3 dimensions. Now this is where slope loses some meaning, of course. So the equation of a line that passes through AB does not change when we're talking about vectors, because vectors could be any dimension. So it's still that. R equals A plus some scalar multiple of the direction vector. A is any point in AB, as I say, B turns out to be the direction vector. So if I want to find the vector equation through these 2 points, bang. Again, I can just write it straight down. I need any point, now I need the direction vector. How did I get it so quick? Whilst it's not slope, I can still use the idea of difference in the x values, difference in the y values, but now also difference in the z values. So I looked at it and I went, 1 minus minus 2 is 3, 2 minus 7 is negative 5, 3 minus 4 is negative 1, and that gave me the direction vector that I was looking for. So what were the Cartesian equation? Now this is where it gets real interesting, because Cartesian equations in 3 dimensions is probably not what you're expecting to see. There it is. What? There's actually 2 equals in there. So basically, it's the rearrangement of this, because remember that R is representing X, Y, Z. It was that same idea that I said before, basically saying, well, they all equal lambda. So when I move this to the other side, I'll get X minus 1, but if I want what lambda is, divide it by the 3. Move the 2 over, we get Y minus 2 divided by the negative 5. Well, I'd change the signs on those. And then we had Z minus 3 divided by the negative 1. Again, I've made it 3 minus Z rather than the negative of Z minus 3. Okay? So Cartesian equations look a little bit different in 3 dimensions. Here's last year's HSC question. So first time it was tested, what did they ask for? So they gave us 2 lines. By equating the components, so that's giving us a bit of a hint on how to do this, find the point of intersection of these 2 lines. Again, reading across for the x values, I get 3 plus lambda 1 is 3 minus 2 lambda 2. Well, straight away I can say, well, lambda 1 is minus 2 lambda 2 from that. Reading across the y values, minus 1 plus 2 lambda 1 is equal to minus 6 plus lambda 2. But we just said lambda 1 was equal to minus 2 lambda 2, so I'll sub that in, and straight away I get that lambda 2 is equal to 1. But I haven't used the z's. What's going on there? Well, let's do the z's. Z plus lambda 1 is equal to 2 plus 3 lambda 2. Solving that, once again I get lambda 2 is equal to 1. So it really depends on the question. They've told me that these lines meet. See, that's the other interesting thing with 3 dimensions. You can have 2 lines that are not parallel, but they may not meet, because you're dealing in 2 to 3 dimensions. Okay? So had they not told me that they actually meet, then I would have had to check and make sure lambda 2 came out to be the same thing for all of them. But in this case, I actually didn't need to. So substituting into the third one confirmed that yes, indeed, these lines do intersect. For this question, we were told the lines intersect, so actually I didn't need to do the third one. So lambda 2 is equal to 1. All right, we still haven't found the point of intersection, of course. So sub into, well, it makes more sense to use the second one because we've found what lambda 2 is. So 3 minus 6, 2 plus minus 2, 1, 3. Add them together. 1 minus 5, 5. Well, that's the vector. I suppose technically they've asked for the point. I should have written, oh, well, it's 1 minus 5, 5. Find the equation of the line that passes through minus 2, 1, 4 and is parallel to this vector. Okay, remember? 2 lines are parallel if they're direction vectors, not necessarily the same, but are scalar multiples of each other. I know it goes through the point minus 2, 1, 4, and I know the direction vector will be some scalar multiple of the direction vector that they've given me. So 2i plus j minus 2k. So that must be the equation of the line. What about if they want perpendicular? So it's the 2 standard questions we've seen in 2 dimensions. You know, find the equation of line parallel, find the equation of line perpendicular. Okay, not as quick this one. 2 lines are perpendicular, in this case, if the dot product of their direction vectors are equal to 0. So the direction vector of the vector I've been given is 1 minus 1, 4. I'm going to dot it with ABC. I've just got to find out what ABC is. So when I do that, I get A minus B plus 4C equals 0. Okay, but here's the other key thing. If they're going to be perpendicular, they have to intersect. So now I solve them simultaneously here. So 0, 2, 3 plus lambda ABC That's the vector equation of the line we're trying to find. And that's got to equal mu 1 minus 1, 4. Let's solve it. Again, break it into its components. I want to find a, b, and c. So 2 plus lambda b is equal to minus lambda a. That gets me that lambda is minus 2 on a plus b. The other one gives me that lambda is 3 over 4a minus c. They've got to be the same, of course. I now get this expression, 11a plus 3b minus 2c is equal to 0. So that gives me another equation I can play with. The one that I had before, well, I've multiplied to make the coefficients of a the same. So 11a minus 11b plus 44c equals 0. I get b is 23c on 7. How do I get the number? But here's the thing. Remember, it's a scalar multiple. So I can pick any number I like to be c, or b for that matter, and then work it out from there. I'm going to pick something that makes the maths nice. So I'm going to let c equal 7. And then that will cancel the fraction. I don't have a denominator. So if I let c equal 7, b is going to be 23. A will then works out to be negative 5. I have my direction vector. So 0, 2, 3 plus lambda minus 5, 23, and 7. If two lines have got these direction vectors, b1 and b2, we know they're parallel if one direction vector is the scalar multiple of the other direction vector. Okay? Perpendicular if those direction vectors have a dot product of 0 and they intersect. If they do neither, then we just say they're skewed. They're skewed lines. So let's show that these two lines are in fact skewed lines. So we need to show that there's no point of intersection, basically, that these will never meet. Okay. Parametrics, 1 plus lambda equals mu. 3 plus lambda is 4 mu, and minus 1 is 5 mu. If they were to intersect, that would be true. If I equate the first one with the third one, I end up with, well, mu is minus a fifth, so lambda becomes minus 6/5. If I equate 2 and 3, I come up with lambda is minus 19 on 5, which does not equal minus 6 on 5. I've come up with two different answers. Therefore, they can't intersect. So as they do not intersect, but the other key thing is they're not parallel, and that's easily to see by inspection because you're just saying, well, the direction vectors are scalar multiples of each other, and they're not in this case. I mean, there's no way 1, 1, 0 and 1, 4, 5 can be created by just multiplying by a number. So therefore, these lines are in fact skewed lines. All right, time to play with vector equations of lines.